The Russian test pilot stood on the tarmac at Shenyang, staring at the aircraft that was supposed to carry him home. It was spring 2006. The J-11B gleamed under the northeastern Chinese Suna. Near-perfect copy of the fighter he'd flown for 20 years. Same distinctive twin-tail silhouette. Same blended wing-body configuration. Same elegant curves that Soviet engineers had spent a decade perfecting. But something was wrong. He'd spent 2 weeks crawling through these aircraft, running his hands along panel gaps, listening to engines spool up, studying turbine blades under microscopes, analyzing data that should have confirmed everything was exactly as it should be. And now, when it came time to climb into that cockpit and fly this machine back to Moscow, a routine flight that should have been nothing more than a formality, he couldn't do it. None of them could. The entire Russian delegation, some of the most experienced Su-27 specialists alive. Men who had collectively logged tens of thousands of hours in flankers boarded a commercial flight home instead. No dramatic announcement, no formal explanation, no diplomatic incident splashed across international headlines. It's just a quiet refusal that sent shockwaves through the global defense industry for those who understood what it meant. What did those engineers discover in those Chinese hangars that made them unwilling to trust their lives to an aircraft built from their own blueprints? What did they see that transformed routine technical consultation into one of the most significant ruptures in modern military aviation history? This is the story of that moment and everything that led to it. Before we dive deep into this investigation, if you find this kind of military aviation analysis valuable, hit that subscribe button. It helps us continue bringing you these declassified stories that reshape how we understand modern warfare. And stay until the end, because what happened after 2006 reveals even more about how nations really operate when technology and trust collide. To understand why Russian engineers refused to fly China's fighter, we need to travel back for decades to a moment when Soviet military planners faced what they genuinely believed was an existential crisis for their nation's air power. The year was 1969. American engineers had just begun work on 2 aircraft that would redefine aerial combat for the next half-century, the F-15 Eagle and F-16 Fighting Falcon. Soviet intelligence operatives had obtained preliminary specifications. What they reported to Moscow sent chills through the highest levels of military command. These weren't incremental improvements over existing American fighters. They represented a technological leap that threatened to render the entire Soviet fighter fleet obsolete overnight. The existing Soviet arsenal, MiG-21s, MiG-23s, Su-15s would be systematically slaughtered against these new American machines. The performance margins weren't close. They weren't even competitive. Something revolutionary was needed, and it was needed urgently. And so the Soviet government issued a requirement for a new air superiority fighter, the PFI, or Prospective NI, Frontovoy Istrebitel, Advanced Frontline Fighter. The specifications were demanding beyond anything previously attempted. This aircraft would need to match or exceed American performance in every meaningful category simultaneously. The Sukhoi Design Bureau drew the assignment. Pavel Sukhoi himself, one of the most brilliant aircraft designers in human history, led the initial conceptual work before his death in 1975. What his team attempted was audacious in scope. Create a fighter that could match America's best in speed, range, maneuverability, weapons load, and radar performance all at once, with no compromises. The first prototype, designated T-10, flew in 1977. Soviet leadership watched with anticipation as their answer to American air superiority took to the skies. The aircraft crashed during testing in 1978, killing test pilot Yevgeny Solovyov. The second and third prototypes revealed severe aerodynamic instabilities that no amount of pilot skill could overcome. Test pilots reported the aircraft was prone to entering uncontrollable spins with little warning. The handling characteristics were unpredictable and dangerous. This wasn't remotely acceptable for a fighter meant to dogfight with the best America could build. Here's where the story takes a critical turn that would echo through decades of aviation history. Mikhail Simonov, who had assumed leadership of the Design Bureau after Sukhoi's death, faced a choice that would determine the future of Soviet aviation. He could incrementally improve the troubled T-10, accepting its fundamental limitations and hoping small refinements would somehow make it competitive. Or he could do something radical, something that would consume years of additional development time and billions of additional rubles. He chose radical. Simonov authorized a complete redesign from the ground up. Everything was reconsidered. Every assumption questioned. The result, designated T-10S first, flew in April 1981. It bore only superficial resemblance to its troubled predecessor. The fuselage was completely reimagined with a distinctive blended wing-body configuration that Soviet aerodynamicists had refined through thousands of wind tunnel hours. Wing area increased by nearly 25%, providing lift and maneuverability characteristics the original design couldn't match. Horizontal stabilizers moved from the wings to the rear fuselage, fundamentally changing the aircraft's stability characteristics. Most critically, the aerodynamic instabilities that had killed Soloviev were eliminated through redesigned control surfaces and a revolutionary analog fly-by-wire flight control system. The aircraft that emerged from this redesign would become known as the Su-27. NATO intelligence officers, following their convention of assigning reporting names to Soviet aircraft, called it the flanker. It would change everything. I've spent years studying Cold War aviation programs, analyzing declassified documents, interviewing engineers and pilots from both sides of the Iron Curtain. And the Su-27 stands out as something truly extraordinary even among the remarkable aircraft of that era. Its development consumed between 12 and 15 billion rubles in 1980s. Currency an astronomical sum that strained even the Soviet economy. But what the Soviets created justified every kopeck. Let me walk you through what made this aircraft revolutionary, because understanding these technical details is absolutely essential to grasping. What happened in that hangar in 2006? The Su-27's airframe was massive for a fighter aircraft, nearly 22 meters long, with a wingspan of 14.7 meters. To put that in perspective, it was substantially larger than the American F-15 it was designed to fight. This wasn't just impressive engineering. It was strategic necessity driven by Soviet geographic reality. That enormous size allowed for internal fuel capacity exceeding 9,000 kilograms, giving the aircraft a ferry range of approximately 3,600 kilometers without aerial refueling. Soviet defense strategy required fighters capable of patrolling from the frozen Arctic to the Pacific coast distances that would exhaust smaller fighters. The flanker could do it without refueling, arriving at any potential conflict zone with fuel to spare for combat. The twin Saturn, AL-31F, afterburning turbofan engines, represented another Soviet triumph. Each produced over 12,500 kilograms of thrust, with afterburner engaged. Combined, they gave the Su-27 something remarkable, a thrust-to-weight ratio exceeding 1:1 in combat configuration. The practical implication was stunning. The aircraft could accelerate while climbing vertically a feat that would cause most Western fighters to stall and fall from the sky. Soviet test pilots demonstrated this capability repeatedly, and Western intelligence officers initially refused to believe the performance claims until they witnessed it themselves. The engine placement was equally clever. Two engines sat unusually far apart, separated by a large space that housed the main landing gear and allowed for weapons carriage beneath the fuselage. This wide separation improved the aircraft's resistance to catastrophic damage. A missile hit on one engine wouldn't necessarily destroy the other, giving pilots a fighting chance to bring their wounded aircraft home. But here's what truly set the flanker apart from anything flying at the time. Soviet engineers had developed a concept they called super maneuverability, the ability to maintain positive control at angles of attack where Western fighters would simply stop flying. The Su-27's combination of massive wing area, powerful flight control authority, and sophisticated fly-by-wire system allowed it to operate in flight regimes that Western aircraft couldn't enter safely. The aircraft could perform the now famous Pugachev's Cobra, pitching the nose up 90 degrees or more while maintaining relatively level flight path, using the entire aircraft as an air brake, then recovering smoothly to normal flight. While tacticians debated endlessly whether such maneuvers had practical combat value, they demonstrated something undeniable: unprecedented flight control authority and aerodynamic capability that no Western fighter could match. The weapon system matched the airframe's ambition. Up to 6 R-7 beyond visual range missiles, plus 4 R-73 short-range infrared missiles, gave the flanker a 10-missile loadout that matched or exceeded any Western fighter. The R-73 in particular was revolutionary, a highly maneuverable infrared missile that could engage targets at extreme angles using a helmet-mounted sight system. Western intelligence was deeply concerned when they learned of this capability. The N-001 MICH coherent pulse Doppler radar could track 10 targets simultaneously and engage 2, providing situational awareness that earlier Soviet fighters lacked. Detection range against fighter-sized targets reached approximately 90 kilometers respectable, though not quite matching the F-15's PG-63 radar. The Su-27 entered service with Soviet air defense forces in 1985. When Western intelligence first observed flankers deployed near Soviet borders, genuine concern rippled through NATO command structures. Fighter pilots who later trained against former Soviet Su-27s after the Cold War made such exchanges possible, universally expressed respect, sometimes grudging, always genuine. One American F-15 pilot described the experience to me years ago. Fighting the flanker was like facing an opponent who was both bigger and more agile than you expected. That combination demanded respect. You couldn't make assumptions. The Soviets had built exactly what they intended, an aircraft capable of dominating any sky it entered, flown by pilots trained specifically to exploit its unique capabilities. And then the Soviet Union collapsed. December 1991, the hammer and sickle came down from the Kremlin for the last time. The Soviet Union dissolved into 15 independent republics. And Russia, the largest successor state, inherited the Su-27, a technological masterpiece built to protect an empire that no longer existed. Russia also inherited catastrophic financial ruin that defied Western comprehension. What happened next in Russian aviation factories was genuinely heartbreaking to those who witnessed it. Facilities that had produced some of the most sophisticated military aircraft in human history were literally running out of electricity because they couldn't pay power bills. Skilled engineers who had designed systems to outfight American F-15s were driving taxis, selling goods in street markets, or leaving the country entirely because defense enterprises couldn't pay salaries for months at a time. The brain drain was devastating. Decades of accumulated expertise walked out factory gates every day, never to return. Test pilots were grounded not because of weather or maintenance issues, not because aircraft were unavailable, but because there was simply no money for aviation fuel. Aircraft that had cost billions to develop sat idle on ramps while their pilots found other work to feed their families. The Komsomolskaya Aviation Production Association (NAPO), which manufactured the Su-27, had capacity to produce dozens of aircraft annually. They received orders for a handful. Production lines designed for mass output sat mostly silent. The Russian Air Force, which had planned to receive hundreds of new flankers throughout the 1990s, could barely afford fuel to keep existing aircraft flying, let alone purchase new production. Its aerospace industry, once a source of national pride and genuine technological achievement, was dying before the world's eyes. And across the border, China was watching. The relationship between Beijing and Moscow had been hostile for decades. The Sino-Soviet split of the 1960s had transformed communist allies into bitter rivals, maintaining massive military forces along their shared border. In 1969, Chinese and Soviet forces had actually exchanged fire in border clashes along the USS Siri River, with casualties on both sides. For a time, nuclear war between the two communist giants seemed possible. Throughout the 1970s and 1980s, Chinese military planners considered the Soviet Union potentially more dangerous than America. But the Soviet collapse changed the strategic calculus entirely. Russia was no longer an ideological rival exporting revolution, was no longer an expansionist military threat positioning forces for potential invasion. It was a struggling post-Soviet state, desperate for revenue, incapable of projecting power beyond its immediate borders, no longer in any position to threaten Chinese security. Chinese leadership, particularly those responsible for military modernization's extraordinary opportunity in Russia's desperate circumstances. For decades, China had struggled to develop modern military technology independently. Despite enormous national efforts, Chinese attempts to design indigenous jet fighters had produced aircraft that were generations behind Western and Soviet designs. The People's Liberation Army Air Force, in the early 1990s, flew aircraft based on Soviet designs from the 1950s and 1960s. Planes China had either purchased during the brief Sino-Soviet alliance or reverse-engineered from examples acquired through various means. The Shenyang J-6, based on the MiG-19. It was essentially a 1950s zero-day fighter that lacked radar entirely and carried only primitive weapons. Thousands had been built, but quantity couldn't compensate for obsolescence. The Chengdu J-7, based on the MiG-21, offered somewhat more capability but still represented 1960s technology. Against modern Western fighters, these aircraft were hopelessly outclassed. Their pilots would be targets, not combatants. More urgently, these aircraft were becoming obsolete compared to equipment operated by China's regional rivals. Taiwan had begun receiving American F-16's modern, capable fourth-generation fighters that would slaughter J-6 South and J-7 South in any aerial engagement. Japan operated F-15 Eagles, among the best air superiority fighters ever built. Even smaller regional powers were acquiring aircraft that outclassed anything in China's inventory. The implications for Chinese military planners were stark and terrifying. If conflict erupted over Taiwan or in the South China Sea scenarios that Chinese strategists planned for constantly, the PLAAF faced systematic destruction by modern Western fighters before it could accomplish any meaningful military objectives. This wasn't theoretical concern. The 1991 Gulf War had demonstrated with brutal, televised clarity exactly what modern Western air power could accomplish against a military equipped with Soviet-era equipment. Chinese military analysts watched in horror as Iraqi forces equipped with aircraft, tanks, and air defense systems very similar to China's own equipment were systematically annihilated by American F-15s, F-16s, and F-A-18s. The Iraqi Air Force barely managed to contest the skies before being swept aside. Ground forces that had seemed formidable were destroyed from the air with minimal American casualties. The message could not have been clearer. China needed modern fighters, urgently. The survival of Chinese military ambitions, perhaps. Chinese security itself depended on closing the technology gap. And Russia, desperate for hard currency, had exactly what China needed. In early 1992, Chinese and Russian negotiators began discussions that would reshape both nations' military futures for decades to come. The Chinese wanted advanced fighters above all else, aircraft that could compete with Western systems and restore meaningful combat capability to the PLAAF. The Russians, desperate for hard currency to keep their aerospace industry alive, were willing to sell systems they would never have considered exporting during Soviet times. The flanker crown jewel of Soviet air power was on the table. November 1992, Russia and China signed their first agreement for direct purchase of Su-27 SK fighters, 24 aircraft, approximately $1 billion. One of the largest Russian arms sales of the chaotic post-Soviet era, the Su-27 SK was an export variant, with systems slightly downgraded compared to aircraft flown by Russian Air Force pilots. Radar capabilities were somewhat reduced. Certain electronic warfare systems were omitted or simplified. The weapons package was more limited, lacking some of the most advanced Soviet missiles. These limitations were standard practice for export variants. No nation sells its absolute best equipment to foreign customers. Nevertheless, for China, the Su-27 SK represented a quantum leap in capability that transformed their strategic position virtually overnight. Consider what this meant for Chinese pilots transitioning from J-7 South to Su-27 SKs. The contrast was almost incomprehensible. The J-7 maxed out at Mach 1.8 at altitude. Its radar, if later variants even had radar at AL, could barely detect targets beyond 30 kilometers. Weapon load was perhaps 2,000 kilograms distributed across 5 hardpoints. Combat radius with external fuel tanks was roughly 700 kilometers. Cockpit was cramped, the avionics primitive, the situational awareness minimal. The Su-27 SK could reach Mach 2.35. Its radar detected and tracked targets beyond 80 kilometers, providing warning and targeting solutions the J-7 pilot could only dream about. It carried up to 6,000 kilograms of weapons across 12 hardpoints. Combat radius exceeded 1,500 kilometers on internal fuel alone, with provisions for aerial refueling extending that further. The cockpit was spacious and well-designed. The fly-by-wire controls made handling intuitive. Aircraft practically flew itself compared to the demanding J-7. The difference wasn't incremental improvement. It was revolutionary transformation. Chinese pilots described the transition like upgrading from an unreliable old truck to a sophisticated racing car with advanced electronics and responsive handling. By 1996, the PLAAF had fully integrated these aircraft into operational units. Their combat capabilities had been transformed from regional laughingstock to serious regional power. Taiwan's pilots could no longer assume aerial superiority. But China's ambitions extended far beyond simply purchasing Russian aircraft off production lines. The Chinese defense industry had perfected a strategy over decades, a patient, methodical approach that had served them well with earlier Soviet technology. Acquire foreign systems through purchase, aid, or other means. Study acquired technology intensively, understanding not just what it did, but how and why. Reverse engineer key components, developing domestic capability to produce them. Modify designs for Chinese requirements and manufacturing realities. Eventually produce fully indigenous versions, eliminating dependence on foreign suppliers entirely. This approach had worked with the MiG-19 and MiG-21, which became the J-6 and J-7 families. Chinese strategists saw no reason the same patient methodology wouldn't work with the Su-27, though they recognized the technological complexity would be far greater than anything they had previously attempted. The flanker represented 1980s Soviet technology, not 1950s or 1960s designs. The gap between understanding and replication would be enormous. In 1995, after successful integration of the first Su-27 SK batch into operational service, Chinese officials approached Russia with a far more ambitious proposal. Instead of continuing to purchase completed aircraft from Russian production lines indefinitely, China wanted to license the complete technology package and establish domestic production capability. This would begin with assembly of Russian-supplied components, then gradually increase indigenization of parts and systems until China could produce the aircraft entirely from domestic sources without any Russian involvement. Russian officials understood perfectly well what China ultimately intended. They had observed China reverse engineer previous Soviet designs. A new licensing Su-27 production would eventually, perhaps inevitably, lead to Chinese competition in export markets. They weren't naive about Chinese strategic intentions, but financial pressures were overwhelming and immediate. While concerns about future competition were distant and theoretical, Russia needed revenue now to keep factories open. The defense industry needed work today to retain skilled workers and maintain production capabilities. Design bureaus needed contracts this year to continue developing next-generation systems. And there was geopolitical calculation as well. Closer defense ties with China could balance against NATO expansion and American power in Asia. Russia needed friends and customers. China was both. December 1996, after more than a year of difficult negotiations, Russia and China signed a licensing agreement that would shape both nations' aviation industries for decades. Shenyang Aircraft Corporation received authorization to assemble 200 Su-27 SK aircraft under license. These Chinese-assembled aircraft would be designated J-11A. The agreement was worth approximately $2.5 billion, one of the largest defense technology transfers of the entire post-Cold War era. The contract's terms were explicit about obligations and restrictions. Russia would supply all major assemblies, airframes manufactured in Russian facilities, AL-31F engines from Saturn, complete avionics packages, weapon systems integration for the full 200 aircraft production run. Russian engineers would provide comprehensive technical documentation covering every aspect of assembly and testing. Chinese production workers would receive extensive training from Russian specialists. Russia would provide ongoing assistance establishing and operating production facilities in China. China would handle final assembly, testing, and delivery to PLAAF operational units. Payment would be structured over the program's life, with initial payments for technology transfer, followed by per-craft payments as planes were completed and accepted. Critically, the agreement explicitly stated that all 200 aircraft would be built using Russian-supplied components. Limited Chinese content was permitted only for non-critical items, wiring harnesses. Some structural fasteners, minor components where Chinese manufacturing was clearly adequate. China agreed not to modify the basic aircraft design without Russian approval. China agreed not to export the aircraft or any derivative of it. China agreed not to use transfer technology to develop competing designs. These provisions were absolutely clear in the contract language. Their enforcement mechanisms were not. No provision for independent auditing of Chinese production, no automatic penalties triggered by violations, no international arbitration process and bilateral discussions between the parties. In practice, Russia would have to detect violations, prove them, and somehow compel Chinese compliance without any institutional framework to support such efforts. The production program launched with considerable optimism on both sides, despite these structural weaknesses. Shenyang Aircraft Corporation invested heavily in new facilities, expanded production halls, modern tooling, and testing equipment. Russian specialists arrived to train Chinese workers on proper assembly procedures, quality control standards, and testing protocols. Cultural and language barriers created friction, but both sides were motivated to make the partnership succeed. The first J-11A aircraft, assembled primarily from Russian components with Chinese labor, rolled out in 1998. It performed well in testing, handling essentially identically to Russian-built Su-27 SKs. Deliveries to PLAAF units began later that year. Chinese pilots reported satisfaction with their new aircraft. For the first several years, everything appeared to function exactly as the agreement intended. Shenyang completed and delivered J-11 as at steady pace, maintaining the production schedule both parties had agreed upon. Component orders flowed to Russian suppliers according to the contracted timeline. Russian factories received regular orders and payments, crucial revenue during Russia's continued economic difficulties through the late 1990s. The partnership seemed to be working. Then the pattern started changing. By 2000, attentive Russian defense industry officials began noticing something troubling in the order flows. Component orders from China were slowing, not dramatically at first, but noticeably. Shenyang had assembled approximately 95 J-11A aircraft by 2003, meaning they should have been ordering components for the remaining 105 aircraft to maintain production continuity and meet the contracted delivery schedule. Instead, component orders dropped significantly. Then they dropped more. Russian suppliers who had expected steady work through 2010 and beyond, who had planned production schedules, maintained workforce levels, invested in capacity based on contracted Chinese orders, found their orders from Shenyang dwindling to a trickle. By 2004, Shenyang Aircraft Corporation had stopped ordering Russian components entirely, not reduced orders, not delayed orders, complete cessation of purchases. Yet satellite reconnaissance showed that production activity at the Shenyang facility hadn't stopped at all. If anything, it had intensified. Russian intelligence agencies began reporting something far more alarming than simple contract violation or payment disputes. Imagery analysts studying satellite photographs detected significant expansion of facilities at Shenyang and at several subcontractor sites throughout northeastern China. New buildings appeared that matched profiles of facilities specialized for composite material production. Engine testing facilities expanded dramatically. New structures consistent with avionics manufacturing centers emerged at multiple locations. Electronic intelligence gathering, monitoring, Chinese communications, and detecting emissions from aircraft systems detected test flights of Su-27, derivatives with system characteristics that matched nothing Russia had ever supplied. The radar signatures were different. Electronic warfare emissions didn't correspond to any exported equipment. Something new was flying over China. The conclusion was inescapable. China hadn't just stopped buying Russian parts due to financial difficulties or contract disputes. They had created an entire parallel program to reverse engineer nearly every major component of the Su-27 SK. What China attempted was extraordinarily ambitious, perhaps the most comprehensive military reverse engineering program since the Soviet Union copied the American Boeing B-29 bomber after World War II. That earlier Soviet effort had consumed years, vast resources, and the talents of thousands of engineers. The Su-27 was far more complex than any 1940s bomber. To understand the true magnitude of what Chinese engineers attempted, you must appreciate the staggering complexity of a modern fighter aircraft. The Su-27 wasn't a simple machine that skilled mechanics could disassemble and copy using basic machine tools. It represented the accumulated knowledge from decades of Soviet aerospace research, thousands of specialized components, advanced materials developed through years of trial and error, Complex manufacturing processes refined over generations of aircraft production and integrated systems that all had to work together with absolute precision. Consider the AL-31F turbofan engine alone, one of the Soviet Union's most significant aerospace achievements and arguably the heart of the flankers' performance. This power plant contained thousands of precision parts operating under the most extreme conditions imaginable. The high-pressure turbine blades had to withstand temperatures exceeding 1,400 degrees Celsius, while rotating at tremendous speeds that would tear apart lesser materials. They were manufactured from specialized nickel-based superlized proprietary formulations developed through decades of Soviet metallurgical research, using sophisticated casting processes that required specialized equipment and extensive expertise. Each blade was then coated with thermal barrier coatings, involving proprietary formulations and application techniques that had taken years to perfect. Simply copying the physical shape of a turbine blade accomplished nothing. You had to replicate the metallurgy, understanding exactly which alloys in which proportions with which trace elements. You had to replicate the casting process, the temperatures, the cooling rates, the mold materials. You had to replicate the coatings, the chemical compositions, the application methods, the curing procedures. You had to replicate the quality control procedures that ensured every blade met specifications. Miss any of these elements, and your engine would fail. Perhaps gradually through accelerated wear, perhaps catastrophically through blade separation at full power. Either outcome was unacceptable. Chinese engineers at Shenyang Liming Aircraft Engine Company faced enormous challenges developing their indigenous version. Designated WS-10, they had actual AL-31F engines to study, complete examples received with the licensed aircraft. They could disassemble these engines completely, measure every component with precision instruments, analyze materials using spectroscopy and electron microscopy, and attempt to recreate manufacturing processes through systematic experimentation. But there's a vast difference between understanding what something is and knowing how to make it reliably. The WS-10 program encountered setback after setback. Early prototype engines suffered compressor surge problems that caused sudden power loss at critical moments. Thrust output fell below specifications. Fuel consumption exceeded acceptable limits, reducing aircraft range and loader time. Reliability remained problematic, with engines failing at rates that would have grounded any operational fleet. Test stands at Liming ran engines for hundreds of hours, attempting to identify and correct problems through systematic analysis. Development consumed years longer than originally planned. Costs far exceeded initial budgets. Western observers watching the program assumed it would fail entirely. But Chinese engineers persisted with characteristic determination, methodically addressing each problem through iterative testing and incremental refinement. The program had national priority status and received whatever resources it required. The flight control system presented equally formidable challenges. The Su-27's analog fly-by-wire system was sophisticated for its era, using multiple redundant channels that voted on control inputs to prevent single-point failures. Complex control laws modulated control surface movements based on airspeed, altitude, angle of attack, pitch rate, roll rate, and dozens of other parameters measured hundreds of times per second. The system had to prevent pilots from overstressing the airframe or entering unrecoverable flight conditions while still allowing full utilization of the aircraft's remarkable aerodynamic capabilities. This required deep understanding not just of the hardware, the computers, the sensors, the actuators, but of the underlying aerodynamic principles and control theory that Soviet engineers spent years developing and testing. Chinese engineers had to reverse engineer not just the physical black boxes containing flight control computers, but the software algorithms running inside them. This proved extraordinarily difficult because the original Soviet code was proprietary and undocumented in any accessible way. Chinese programmers had to analyze system behavior under countless flight conditions, carefully measuring inputs and outputs to infer the control laws from observed responses. They then had to write their own software code that would produce similar results, test it extensively in simulators and on actual aircraft, and modify it repeatedly based on flight test results. The process required years of painstaking work and hundreds of test flights, each one risking pilot lives on software that might contain subtle errors only revealed under specific conditions. The avionics suite demanded similar comprehensive effort across radar, navigation, communication, electronic warfare, and weapons integration systems. Each subsystem involves specialized technologies, proprietary techniques, and complex integration requirements that couldn't simply be copied by examination. The N-001 MICH radar used a Cassegrain antenna design with specific RF characteristics that required precise replication. The signal processing hardware and software had to be recreated to provide comparable detection ranges and tracking capabilities against targets in realistic combat environments. Beyond these major systems, thousands of smaller components needed attention. Hydraulic actuators controlling flight surfaces, fuel pumps maintaining precise flow rates under varying conditions, electrical generators providing stable power, environmental control systems keeping pilots and electronics at survivable temperatures, landing gear mechanisms handling the stress of carrier-weight aircraft impacting runways, cockpit displays providing pilots with essential information, ejection seats capable of saving lives in emergencies, weapons pylons strong enough to carry missiles through violent maneuvering. Every single item had to be either successfully reverse-engineered or sourced from Chinese suppliers capable of meeting the demanding specifications. The entire supply chain had to be created or adapted. Quality control procedures had to be established, ensuring components met standards that Soviet industry spent decades developing. This represented an enormous national commitment of resources and talent. Thousands of engineers and technicians worked on various aspects of the program across dozens of facilities. Specialized testing infrastructure was built or expanded throughout China. Universities and research institutes contributed expertise in materials science, aerodynamics, propulsion, physics, electronics, and numerous other disciplines. The Chinese government invested billions of yuan over many years, treating the program as a strategic priority essential to national defense and long-term industrial development. By 2004, Chinese engineers had achieved sufficient success across enough systems that Shenyang could begin producing what they designated the J-11B. The J-11B looked almost identical to the Su-27 SK and J-11A from external observation. Same distinctive silhouette, same dimensions, same paint schemes. But inside, this aircraft incorporated Chinese-designed and Chinese-manufactured engines, avionics, flight control computers, and numerous other systems. Chinese engineers viewed the J-11B as proof their nation could master advanced aerospace technology and break free from dependence on foreign suppliers. They were proud of what they had accomplished against difficult odds. Russian officials viewed it as wholesale theft of intellectual property on a massive scale of flagrant violation. Of every commitment China had made in the licensing agreement, the Chinese perspective differed significantly from Moscow's interpretation. Chinese officials argued the Su-27 SK technology was becoming obsolete, which was partially true, as the basic design dated to the early 1980s, and that Russia had failed to provide promised upgrades and technical support that would have kept the aircraft competitive. They claimed the license agreement gave them rights to modify and improve the basic design for their own operational needs. National security imperatives, they insisted, demanded indigenous production capabilities rather than permanent dependence on foreign suppliers who might someday become adversaries again. This fundamental disagreement about the contract's scope and China's rights would poison the bilateral relationship for years to come. By 2006, the situation had reached critical mass. Russian intelligence had compiled extensive evidence documenting Chinese reverse engineering efforts in embarrassing detail. Satellite imagery showed expanded production facilities at Shenyang that far exceeded what licensed assembly would require. Electronic intelligence detected J-11 variants flying with systems that had never been delivered by Russia. Commercial intelligence indicated China was beginning to market derivatives of Su-27 technology to potential export customers in the developing world, directly competing with Russian offerings. The Russian Defense Industry Sukhoi Design Bureau, Rosoboron, Export State Arms Export Agency, Saturn Engine Company, was collectively furious. China had apparently violated a multi-billion-dollar licensing agreement through systematic deception. Worse, they were now potentially competing with Russian export sales using technology that had been stolen from Russia. Revenue that should flow to Russian enterprises would instead go to Chinese competitors offering knockoff products. The Russian government decided to send a technical delegation to Shenyang. The official purpose described in diplomatic communications, technical consultation on the licensed production program, and discussion of potential future cooperation on advanced systems, the real purpose, understood by everyone involved, investigation and documentation. The Russian government wanted to see exactly what China had built, assess its quality and capabilities, determine whether the cooperation relationship could somehow be salvaged, or whether it should be formally terminated with maximum diplomatic consequences. The delegation that landed at Shenyang in spring 2006 wasn't composed of junior technicians, mid-level bureaucrats, or diplomatic functionaries. These were some of the most experienced Su-27 specialists, alive men whose professional lives had been devoted to the flanker. The team included senior engineers from Sukhoi's design bureau who had worked on the original T-10 and T-10S prototypes, who understood every design decision that had produced the Su-27. There were production specialists from the KNAP factory in Komsomolsk-on-Amur, the facility that had manufactured Russian Su-27 variants for 2 decades, who knew every detail of how the aircraft was supposed to be built, what proper workmanship looked like, what deviations indicated problems. Representatives from Saturn Engine Company joined the delegation to evaluate propulsion systems, men who had built AL-31F engines with their own hands and could spot manufacturing deficiencies instantly. Officials from Rosaboron Export attended to assess commercial and diplomatic dimensions. Several test pilots with thousands of hours in Su-27 variants accompanied the technical specialists. These weren't people who could be fooled by fresh paint, impressive facilities, or confident marketing presentations. They had spent entire careers with the Su-27 in all its variants. They knew what the aircraft should sound like during engine start, the exact sequence of whines and roars as systems spooled up. They knew how hydraulics should respond during control checks. They knew what the flight control system should feel like during taxi, the subtle feedback through the stick. They knew which instrument readings indicated normal operation and which suggested underlying problems. They could identify manufacturing quality issues simply by running their hands along panel gaps and feeling for irregularities. They could hear potential engine problems and frequencies that less experienced personnel would never notice. What they found at Shenyang genuinely shocked even these experienced specialists, men who had believed they knew what to expect. The Chinese weren't just assembling Russian components anymore under the original licensing agreement. They had created entire parallel production infrastructure that replicated nearly every aspect of Su-27. Manufacturing from raw material processing through final assembly and test, Chinese engineers proudly showed their Russian visitors what they had accomplished. Domestically produced airframe sections fabricated from Chinese materials, Chinese-designed avionics bays with locally manufactured electronics, indigenous flight control computers running Chinese software, WS-10 engines that China claimed matched or exceeded the performance of Russian AL-31F power plants. The Russian engineers requested detailed examination of several J-11B aircraft. They wanted to inspect internal structures normally hidden from view. They wanted to review manufacturing documentation and quality control records. They wanted to examine material certifications and specifications. They wanted flight test data. The Chinese, confident in their accomplishments after years of determined effort, agreed to these examination requests. They believed they had successfully replicated the Su-27's capabilities and improved upon Russian designs in several areas. They wanted to demonstrate their technical prowess to the visitors from Moscow. The Russian team spent approximately 2 weeks conducting meticulous inspections using equipment they had brought specifically for this purpose. They examined airframe structures in detail, joint quality, where major sections connected, fastener installations throughout the aircraft, composite layup procedures used for structural panels, coating applications, protecting surfaces from corrosion and heat. They photographed everything. They reviewed engine specifications exhaustively. Turbine blades examined under high-magnification microscopes for metallurgical defects. Tolerances checked with precision measuring instruments calibrated to Russian standards. Test data analyzed for performance trends and reliability indicators. They took notes constantly. They studied avionics installations systematically. Software responses tested under various simulated conditions. Display quality evaluated. Systems integration verified through multiple test scenarios. They documented anomalies. They interviewed Chinese engineers and production workers, asking detailed questions about manufacturing processes, quality control procedures, and testing protocols. The answers were sometimes confident, sometimes evasive, sometimes revealing. What they discovered during those examinations raised serious concerns about quality control and manufacturing standards that went beyond simple differences in national approach or acceptable variation. According to multiple sources familiar with the inspection results, though specific details remain officially classified by both governments, the Russian team identified numerous deviations from original Su-27 specifications throughout the aircraft they examined. Some deviations represented attempted improvements that might or might not prove effective in actual service. Chinese engineers trying to enhance performance beyond the original design. Others appeared to be cost-cutting measures that potentially compromised performance characteristics or long-term service. Life substituting cheaper materials or simpler processes for more expensive Soviet specifications. Most troublingly, some deviations seem to result from incomplete understanding of original engineering. Principles Chinese engineers not fully grasping why certain specifications existed and what problems they prevented. The composite materials used in certain structural components didn't match the specifications of original Russian materials in fiber content, resin formulation, or layup procedures. Not necessarily catastrophic in the short term, but raising serious questions about long-term structural integrity under the repeated stress cycles of combat maneuvering and carrier qualification landings. The flight control software had been extensively modified from the original Soviet code, necessarily so. Since Chinese engineers had written it from scratch based on observed behavior, but the Russian engineers couldn't verify whether those modifications properly accounted for all the complex aerodynamic behaviors that original Soviet engineers had spent years testing and refining through painful experience. The margins in fly-by-wire systems are thin. Software that works perfectly in 99 flight conditions might fail catastrophically in the 100th. Most concerning to the Russian specialists were the engines. The Chinese WS-10 was supposed to match or exceed the Russian AL-31F in all performance parameters. That was the claim. Russian engine specialists found significant differences in manufacturing quality that their experience told them would have serious consequences. Turbine blade tolerances weren't as precise as Russian standards required. Variations that might seem tiny in absolute terms, but accumulated across hundreds of blades to create imbalances and uneven heating. Heat-resistant coatings appeared thinner and less uniform than the exacting Soviet specifications variations. That would accelerate thermal degradation under combat power settings. The manufacturing processes showed evidence of shortcuts that might reduce production costs, but would certainly reduce service life. The Russian engineers performed calculations based on their observations. They estimated these engines would have significantly shorter service lives than properly manufactured. AL-31F power plants perhaps requiring overhaul or replacement at intervals that would severely impact operational availability. More concerning, they predicted less reliable performance under the extreme conditions of combat maneuvering high-G turns. Afterburner at maximum altitude, rapid throttle movements during dogfighting, exactly the conditions where engine failure would be most likely to kill pilots. There's a crucial technical point requiring explanation here, because it illuminates why the Russian engineers reacted as they did. Modern fighter aircraft operate at the absolute edge of what's physically possible. The margins between optimal performance and catastrophic failure are incredibly thin, far thinner than in any civilian aircraft. Any automobile, any machine most people ever encounter. Every component must be manufactured to exacting specifications, because small deviations can cascade into major problems through mechanisms that only experienced engineers fully understand. When you're pulling 9G turns at supersonic speeds with dozens of tons of thrust pushing you through air that's simultaneously lifting your wings and trying to tear them off, your life depends on every rivet, every weld, every software subroutine being exactly right. There's no margin for almost good enough. The Russian delegation spent 2 full weeks examining aircraft, reviewing production facilities, and discussing the situation with Chinese counterparts in meetings that ranged from technical sessions to diplomatic conversations. The Chinese engineers remained proud of what they had accomplished despite the visitors' obvious concerns. From their perspective, they had successfully indigenized advanced technology against tremendous odds and made improvements in several areas. Their avionics were demonstrably more modern than original Russian systems. They had reduced weight in some structural areas through innovative manufacturing, Domestic production meant they were no longer dependent on Russian supply chains that might be interrupted by political disagreements. They had achieved exactly what China's national strategy demanded. Then the time came for the Russian delegation to return to Moscow. The Russian delegation had arrived in China aboard a standard commercial flight, as was normal for such technical consultations. The original plan discussed and agreed upon before the visit called for some team members to fly back to Russia aboard a J-11B aircraft, so it would demonstrate continued confidence in Chinese production quality. It would maintain the useful fiction that the licensing agreement still functioned normally. It would provide Russian pilots with direct experience of the Chinese-built variant for technical assessment purposes. Instead, when departure day arrived, the entire Russian delegation boarded a commercial flight home.
Oh.
Every single member, engineers, pilots, officials, all of them choosing airline seats over a flanker cockpit. No formal announcement accompanied this decision. No dramatic confrontation occurred on the tarmac. No strongly worded diplomatic protest was lodged through official channels. The Russian engineers simply declined the planned flight, citing scheduling complications and other technical commitments that required their presence in Moscow. But within the tight-knit global community of military aviation professionals, the message was absolutely unmistakable. It spread through informal channels within days. Russian specialists, the foremost Su-27 experts in the world. Men who had spent careers with these aircraft had examined China's reverse-engineered flanker in exhaustive detail. They had reviewed the manufacturing, they had evaluated the systems, they had analyzed the engines, and they had concluded it wasn't safe enough to trust with their lives. The consequences of that quiet refusal were immediate, severe, and long-lasting. Within months, Russia officially suspended all military aviation technology cooperation with China. The license production agreement for the J-11A was declared violated and formally terminated. Russia withdrew technical support for aircraft. China had already received no more spare parts through official channels, no more engineering consultations, no more software updates. More significantly, Russia refused to sell China any more advanced systems requests that had been under negotiation for years. The Su-33 carrier-based fighter China had wanted for its developing aircraft carrier program. Denied. Russia wouldn't provide the aircraft or the technology to adapt land-based flankers for carrier operations. The Su-35, with its more powerful engines, thrust vectoring nozzles, and advanced avionics representing the latest flanker evolution, is not available for export to China at any price. Advanced air-to-air missiles that would have given Chinese fighters beyond visual range capabilities matching Western systems is no longer for export to Chinese customers. The relationship between Russian and Chinese defense industries, which had seemed so promising in the desperate 1990s, which had generated billions in revenue, which had transformed Chinese military capabilities, essentially froze solid. This freeze lasted nearly a decade. Trust, once broken so comprehensively, proved extraordinarily difficult to rebuild. During those frozen years, China doubled down on indigenous development with renewed determination. Programs to design and build aircraft entirely without Russian assistance received increased funding, priority status, and the nation's best engineering talent. If Russia wouldn't sell China advanced systems, China would build its own. Russia turned to other export markets, particularly India, which became Russia's largest arms customer, and various Southeast Asian nations to replace the massive revenue stream that Chinese purchases had provided. Russian diplomats and salesmen emphasized to these new customers that Russia respected intellectual property agreements and would support exported systems throughout their service lives. The implicit message about China required no elaboration. What does this incident reveal about both nations' aerospace industries and their broader strategic calculations? The Russian position was straightforward in its logic. China had committed industrial espionage on massive scale, systematically violating contract terms and stealing intellectual property that cost the Soviet Union and Russia billions of dollars and decades of intensive research to develop. From Moscow's perspective, this wasn't just about one aircraft program, however valuable. It was about whether China could be trusted as a partner in any sensitive technology transfer. The answer, clearly, was no. The Chinese position, though less publicly articulated, rested on arguments that Beijing's strategists found equally compelling. The technology transfer agreement gave China certain rights to modify and improve the basic design rights, whose scope was genuinely ambiguous in the contract language. Russian production quality and technical support had been inadequate, forcing China to develop domestic alternatives simply to keep aircraft flying. National security imperatives demanded independent production capabilities rather than permanent dependence on foreign suppliers who might become adversaries again, as the Soviet Union had been within living memory. Both positions have genuine merit, which makes this case so analytically complex and interesting. International technology transfer agreements in the defense sector occupy an uncomfortable gray area between normal commercial contracts, where terms are enforced through courts and arbitration, and national security policy, where sovereignty, strategic autonomy, and balance of power between nations override contractual niceties. Unlike civilian technology, where everyone benefits from widespread adoption, military systems inherently involve questions of relative power. When Russia sold China the right to produce Su-27s domestically, they were inherently transferring knowledge that could enable future independent development. Where exactly the line should fall between legitimate technology transfer and illegitimate reverse engineering remains genuinely disputed by reasonable analysts. What's particularly striking when comparing this case to other international military aircraft programs? Such partnerships rarely work as intended over the long term. Consider the F-35 Joint Strike Fighter, where America has maintained extremely strict technology control even with its closest allies. Partner nations pay billions for aircraft, but receive limited access to source code, maintenance data, and upgrade pathways. They accept these restrictions because American technology is worth the constraints. Consider European collaborative programs like the Eurofighter Typhoon, which required elaborate workshare agreements to manage intellectual property among partners who fundamentally trusted each other based on decades of alliance. Even with that trust, disputes over technology sharing created constant friction. The Su-27 licensing agreement between Russia and China lacked both the strict controls of American export programs and the institutional trust frameworks of European collaboration. Russia needed money, but rightly feared reverse engineering. China wanted technology, but resented supply chain dependence that could become strategic vulnerability. Neither side fully trusted the other's long-term intentions. Neither had legal or political mechanisms to enforce their preferred interpretation of deliberately ambiguous contract language. The outcome, in retrospect, was probably inevitable from the moment the agreement was signed. From purely technical standpoint, the Russian engineers' concerns about the J-11B appear to have been validated by subsequent events, though definitive data remains difficult to obtain given Chinese secrecy about military accident rates. Throughout the late 2000s and early 2010s, the Chinese Air Force experienced several serious accidents involving J-11 variants that became known despite official secrecy. While accident rates for any fighter fleet are genuinely difficult to compare across nations' different operating conditions, different training intensities, different reporting transparency, multiple independent aviation analysts noted that J-11s seem to have elevated rates of engine-related incidents compared to Russian-operated Su-27 SK counterparts flying similar mission profiles. The Russian engineers had predicted exactly such problems based on what they observed in Shenyang. China's response to these challenges was characteristically determined and well-resourced. Rather than scaling back indigenous fighter programs or quietly returning to Russian suppliers, Chinese leadership accelerated domestic development efforts. The J-11B evolved into the J-11D, incorporating more advanced systems developed through continued iteration. The J-15 carrier fighter, another Su-27 derivative, reverse-engineered from an Su-33 prototype China had acquired through Ukrainian Terran service despite Russian refusal to provide any assistance with carrier aviation technology. The J-16 strike variant incorporated even more sophisticated Chinese-developed systems for precision ground attack and electronic warfare. Each generation showed measurable improvements in manufacturing quality, systems integration, and overall capability. Problems identified in earlier variants were systematically addressed through engineering refinement and quality control improvement. The WS-10 engines that Russian engineers had criticized in 2006 gradually matured into genuinely reliable power plants through iterative development and massive investment in manufacturing infrastructure. By the mid-2010s, something remarkable had occurred that vindicated Chinese strategy even as it confirmed Russian fears. China had established a fully indigenous production chain for advanced fighter aircraft. It no longer needed Russian components, Russian engines, Russian expertise for anything. The J-25th generation stealth fighter entering service in 2017 represented capabilities that Russia itself struggled to match with its own next-generation programs. Chinese engineers had learned enough from the flanker program to leap beyond their teachers. This success came at enormous cost, both financial and diplomatic. China's defense budget had grown exponentially, providing resources to sustain development programs that would have bankrupted smaller nations. The rupture with Russia, while eventually partially healed by geopolitical necessity, fundamentally changed how both nations approached defense cooperation. Russia became far more cautious about technology transfers, even to traditional partners like India. Export variants were more carefully controlled. Licensing agreements, when offered at all, contained far more restrictive provisions with actual enforcement mechanisms. China became even more committed to technological self-sufficiency, even when foreign alternatives might be cheaper or more readily available. The lesson of 2006 that foreign suppliers could cut you off when political circumstances changed was not forgotten. The irony of this story is that by 2015, Russia and China were negotiating arms deals again. It's time Russia agreed to sell China the Su-27, one of the most advanced flanker variants ever produced. With thrust vectoring engines, significantly improved radar, and combat capabilities exceeding anything China had yet demonstrated with indigenous designs. Why would Russia sell advanced aircraft to a nation that had so blatantly reverse-engineered their previous export and violated explicit contractual commitments? The geopolitical landscape had transformed since 2006. Western sanctions imposed over Russia's annexation of Crimea and intervention in Ukraine left Moscow increasingly isolated from European markets and technology. Russia needed economic partners who wouldn't enforce American-led sanctions regimes. China was the obvious choice: large, wealthy, and increasingly hostile to American dominance. China, despite substantial indigenous capabilities, still valued access to Russian engines and certain specialized technologies where Russian expertise remained superior. The WS-10 worked, but the latest Russian engines offered performance advantages worth acquiring. Both nations faced a common strategic competitor in the United States, finding renewed alignment against what they perceived as American hegemony. They discovered renewed value in cooperation, albeit with far more explicit contractual protections and enforcement mechanisms than the naive agreements of the 1990s. The incident in 2006 had accelerated Chinese technological independence while simultaneously damaging the partnership that enabled China's initial breakthrough. It became a case study taught in defense industry courses about how military technology transfer operates under fundamentally different dynamics than civilian commerce. When you sell someone a passenger aircraft, you want them to operate it successfully, and hopefully buy more. When you sell someone a fighter jet, you're always aware they might someday use that technology against you in combat or use it to compete against your other export sales in markets you depend upon for revenue. The Russian engineers' refusal to fly that J-11B back to Moscow was based on technical assessment of immediate safety concerns. But the strategic implications of their decision extended far beyond any individual's personal safety. Their quiet refusal publicly signaled to everyone in the global defense industry paying attention: Russian specialists didn't trust Chinese manufacturing quality with their own lives. These weren't random critics or competitors with axes to grind. These were the world's foremost Su-27 experts, men who had built and flown flankers for decades. Their professional judgment carried weight. That message resonated through defense ministries and procurement offices worldwide. Countries considering Chinese military aircraft for their own air forces had to wonder if Russian engineers who knew the original design intimately wouldn't fly the Chinese copy, why should anyone else trust their lives to it? This reputational damage probably set back Chinese defense exports by years. During the late 2000s, when China aggressively marketed the J-10 fighter and various other indigenous designs to developing nations seeking affordable modern aircraft, potential customers frequently cited quality and reliability concerns. Some of those concerns traced directly to the J-11 controversy and what it revealed about Chinese manufacturing standards. Chinese defense manufacturers eventually responded by dramatically improving quality control processes. increasing transparency about manufacturing procedures, and offering extensive warranties and support packages that reduced customer risk. By the 2010s, Chinese military aircraft were winning export orders in Pakistan, Bangladesh, Myanmar, and several African nations looking for capable aircraft at prices below Western alternatives. But the shadow of those earlier quality questions lingered in procurement discussions for years. What lessons can we draw from this complex episode spanning decades of aerospace history? First, intellectual property protection and defense technology transfer requires far more than contracts and written agreements. It requires mutual trust developed over years of reliable partnership. It requires transparent oversight mechanisms with real enforcement capability. It requires genuinely aligned strategic interests where both parties benefit from the relationship continuing successfully. Russia and China in the 1990s had none of these foundations in adequate measure. Their partnership was transactional from the beginning, Russian desperation for cash, meeting Chinese desperation for technology. Such foundations cannot support lasting cooperation when interests diverge. Second, reverse engineering is not simply copying. It requires deep understanding of engineering principles underlying the original design. It requires extensive testing to validate that copies actually perform as originals do. It requires years of iterative improvement as problems emerge in service. China ultimately succeeded in creating indigenous Su-27 variants that matched and eventually exceeded Russian originals in some respects. But the process took far longer and cost far more than simply continuing to purchase Russian aircraft would have. The choice to pursue independence was strategic, not economic. Third, technological dependencies in defense create strategic vulnerabilities that nations will pay almost any price to escape. China's determination to achieve independence from Russian suppliers, Evan, when that independence was more expensive and more time-consuming than continued imports, would have been reflects how seriously nations take defense industrial autonomy when they believe their survival may someday depend on it. Russia's willingness to cut off a major customer to protect intellectual property and maintain technological advantages shows similar priorities from the opposite perspective. Both nations acted rationally according to their strategic interests. Looking from today's vantage point, the aftermath appears mixed for both participants. China achieved its goal of indigenous fighter production capability, an achievement of genuine significance that transformed its strategic position in Asia. But China damaged its international reputation for respecting intellectual property agreements and delayed its defense export ambitions by years. Other potential partners watched what happened to Russia and drew conclusions. Russia protected its intellectual property from further exploitation and maintained leverage over advanced aerospace technology. But Russia lost a massive customer providing desperately needed revenue during difficult years, and ultimately pushed China toward becoming a capable competitor rather than remaining a dependent partner. Russian aerospace firms that expected decades of Chinese orders found themselves seeking alternative markets. The Su-27 family remains in production in both countries today, with Russian and Chinese variants diverging increasingly in capabilities, systems, and design philosophy. The most profound and lasting impact may be on how both nations approach international defense cooperation today. Russia now insists on far more restrictive technology transfer terms than it accepted in the optimistic 1990s. Licensing agreements for domestic production are rarely offered anymore. Russia prefers direct sales of completed aircraft where technology transfer is minimized. When production licenses are occasionally granted, the contracts contain detailed enforcement provisions, audit rights, and penalty clauses that the original Chinese agreement lacked. China has learned its own lessons about technology transfer, having experienced attempts by countries like Pakistan and Iran to reverse engineer Chinese military systems, exactly as China reverse engineered Russian ones. The student became the teacher and discovered that teaching has costs when students prove too capable. Both nations emerged from the J-11 experience with hard-won understanding of how genuinely difficult managing military technology partnerships can be. For students of aviation history and military technology, this incident offers crucial insights into how geopolitics, economics, and engineering interact in the defense sector in ways that don't occur in civilian industry. The Su-27 was designed in the 1970s specifically to counter American air superiority to ensure Soviet pilots could fight and win against F-15s and F-16s defending NATO airspace. 40 years later, Reverse-engineered Chinese copies of that Soviet design fly alongside fully indigenous Chinese fifth-generation stealth fighters. While Russia itself struggles to field comparable numbers of its own next-generation aircraft due to economic constraints and production difficulties, the aircraft that was supposed to cement Soviet technological dominance instead became the foundation for China's emergence. As a major aerospace power challenging both Russia and America in the 21st century, when I think about those Russian engineers standing on the tarmac at Shenyang in spring 2006, I imagine the difficult conversations they must have had among themselves in the preceding days. They were looking at an aircraft based on a design their colleagues had created through years of painstaking effort. They saw familiar shapes, the distinctive twin tails, the blended wing body, the elegant curves they knew so well. They saw familiar systems, what appeared to be familiar systems. But they also saw deviations from specifications they had memorized decades ago. They saw modifications whose implications they couldn't fully assess. They saw manufacturing quality that raised questions they couldn't answer with confidence. The decision not to fly that aircraft back to Moscow wasn't theatrical gesture or political statement in the moment it was made. It was experienced professionals making a safety judgment based on what they had observed with their own eyes and measured with their own instruments. But that quiet judgment, that simple choice to take a commercial flight instead crystallized. Years of growing tension between two nations and fundamentally altered the trajectory of Sino-Russian defense relations for a generation. The J-11 saga demonstrates conclusively that in military aviation, technology is never just technology. It's wrapped inextricably in questions of national pride, strategic autonomy, economic development, and geopolitical power that transcend engineering specifications. The flanker's elegant airframe, which Soviet engineers designed to dominate European skies in a war that fortunately never came, became vehicle for Chinese industrial ambition and source of Russian resentment. The same aircraft that brought Russia and China together as partners in the desperate 1990s ultimately pushed them apart as competitors in the strategic 2000s. Today, Russian Su-27 variants and Chinese J-11 derivatives patrol opposite sides of the Pacific Ocean, facing different adversaries, serving different strategies, both descendants of that same brilliant Soviet design conceived in the 1980s to counter American power. Their parallel evolution tells us something profound about how technology spreads across borders despite every effort to contain it, about how nations pursue strategic advantage through any means available, about how even the closest partnerships built on mutual necessity can fracture catastrophically when underlying interests diverge. The Russian engineers who refused to fly that J-11B home to Moscow had no way of knowing they were marking a turning point in global defense industry relationships that analysts would study for decades. But history has proven their caution was both technically sound and strategically significant in ways that extended far beyond their immediate safety concerns. The story of the J-11 is ultimately about more than one aircraft program or one diplomatic incident in 2006. It's about how nations navigate the dangerous waters between cooperation and competition, between trust and justified suspicion. When the technology involved can determine their survival in future conflicts, no one can yet predict. It's about the enormous price of technological independence and the equally enormous cost of betrayed trust. And it's a permanent reminder that in the world of military aviation, where margins between success and disaster are measured in millimeters and milliseconds, every decision carries weight far beyond the immediate moment. Those Russian engineers stood on that tarmac, staring at a near-perfect copy of their life's work. They knew what they had built. They knew what they were looking at. And they walked away. That walk changed everything.